Subnet in IP network. A subnet, short for subnetwork, is a logical subdivision of an IP network. The process of dividing a single large network into smaller, more manageable parts is called subnetting. Purpose of subnetting. Subnetting is a fundamental practice in IP networking used for several key reasons: efficiency and organization. It organizes a large network into smaller, more efficient segments. Reduced broadcast traffic. In a single large network, all devices receive every broadcast message. Subnetting confines broadcast traffic within its own subnet, reducing network congestion and improving overall performance. Security. Subnetting allows administrators to isolate sensitive areas of a network, example separating a finance department's subnet from a guest Wi-Fi subnet, and apply specific security policies, firewalls, at the boundaries between subnets. Easier management. It simplifies management by grouping devices logically, example all printers in one subnet, all servers in another. Optimizing IP address allocation. Subnetting helps utilize the limited IPv4 address space more efficiently by matching the size of the subnet to the actual number of hosts required in that segment. How subnetting works: network ID versus host ID. The concept relies on how an IP address is structured. An IP address is logically divided into two parts: one, network ID, the portion of the address that identifies the specific subnet or network the device belongs to. All devices within the same subnet share the same network ID too. Host ID, the portion of the address that uniquely identifies a specific device, host, within that particular subnet. Subnetting works by borrowing bits from the host ID portion of the IP address to create a new, extended network ID. The role of the subnet mask. The subnet mask is the key tool used to distinguish the network ID from the host ID. A subnet mask is a 32-bit number, for IPv4, that works in tandem with the IP address. It uses a sequence of ones to indicate the bits that belong to the network ID and a sequence of zeros to indicate the bits that belong to the host ID. When a router or host performs a bitwise AND operation between the IP address and the subnet mask, the result is the network address of that subnet. Example: consider a device with an IP address of 192.168.1.10 and a standard subnet mask of 255.255.255.0, also written as /24 in CIDR notation. The 255.255.255 part, the first 24 bits, identifies the network, 192.168.1.0. The 0.0 part, the last 8 bits, identifies the specific host, 0.10, within that network. Any device with an IP address starting with 192.168.1.x is on the same subnet in this configuration. Devices in the 192.168.2.x range would be on a different subnet. Communication between different subnets always requires a layer 3 device, a router. Subnet calculation. Calculating a subnet involves determining how many bits to borrow from the host portion of an IP address to create new network IDs, based on the requirements for the number of subnets needed or the number of hosts needed per subnet. This calculation is governed by the subnet mask and binary mathematics. Here is a step-by-step explanation of how subnets are calculated, focusing on the common IPv4 environment. Key concepts for calculation. The calculation relies on the relationship between IP addresses, subnet masks, and binary powers of 2, CIDR notation, / notation. This is a shorthand that indicates how many bits are used for the network portion of the address. Example: /24 means the first 24 bits are network bits. Subnet mask, a 32-bit number used to differentiate the network and host. Portions. Formula for hosts: 2^(h2), where is the number of available host bits, calculates the number of usable host IPs in a subnet. The two addresses subtracted are the network address, all host bits are 0, and the broadcast address, all host bits are 1. Formula for subnets: 2^, where is the number of borrowed subnet bits, calculates the number of subnets created. Step-by-step subnet calculation. Example: 192.168.1.0/24, let's say you start with the network 192.168.1.0/24 and you need 4 usable subnets of equal size. Step 1, analyze the starting network address, 192.168.1.0 subnet mask, 255.255.255.0/24, total bits, 32 bits total. Network bits, 24, all ones in the mask. Host bits, 8, all zeros in the mask, in the 4th octet. Step 2, calculate the required subnet bits, s. You need to find the smallest power of 2 that accommodates the required number of subnets, 4. 2^1 equals 2, not enough, 2^2 equals 4, enough. You need to borrow 2 bits from the host portion of the address. Step 3, determine the new subnet mask and CIDR. You increase the network bits by the number of bits borrowed. New network bits equals original network bits plus borrowed bits equals 24 plus 2 equals 26. New CIDR notation, /26 new subnet mask, the first 26 bits are 1. In binary, with the new 26 network bits underlined 111111111111111111111111111111111111111111111 in decimal, this mask is 255.255.255.192. Step 4, calculate hosts per subnet, H, calculate how many host bits, H, remain after borrowing, remaining host bits equals original host bits, borrowed bits equals 82 equals 6 bits. Calculate the number of usable hosts per subnet, 2(2 equals 2(6) 2 equals 64 2 equals usable hosts. Step 5, list the new subnets, network addresses, the new subnets increase by a fixed block size or magic number. The block size is determined by the value of the rightmost borrowed bit in the subnet mask. In our new subnet mask, 11000000, the on bits are 128 and 64. The rightmost borrowed bits value is 64. The new subnets for the 192.168.1.0/24 network will start every 64 addresses. Subnet network address first usable host last usable host broadcast address ID subnet 1192.168.1.0 192.168.1.1192.168.1.62 192.168.1.63 subnet 2 192.168.1.64 192.168.1.65 192.168.1.126 192.168.1.127 subnet 3 192.168.1.128 192.168.1.129 192.168.1.190 192.168.1.191 subnet 4 192.168.1.192 192.168.1.193 192.168.1.254 192.168.1.255 By following these steps, you have successfully calculated 4 distinct subnets from a single Class C network block. Private IP addresses and public IP addresses. In IP networking, addresses are categorized as either private or public, defining their scope and routability within the Internet ecosystem. Public IP addresses. A public IP address is a globally unique identifier assigned to a device by an Internet Service Provider, ISP, that allows it to communicate directly over the Internet. Globally routable, public IP packets can be routed across the entire Internet. Unique, every public IP address currently in use is unique across the globe, preventing conflicts. Assignment. These addresses are managed and allocated by global and regional governing bodies like the Internet Assigned Numbers Authority, IANA, and regional Internet registries, RIRs, and then assigned to end users by ISPs. Use cases: web servers, email servers, and home routers, on their external interface, typically use public IPs so they can be accessed from anywhere in the world. Security: because they are directly exposed to the Internet, devices with public IPs are more vulnerable to external security threats and require firewalls and other security measures for protection. Private IP addresses. A private IP address is used for communication within a local area network, LAN, such as a home, office, or corporate network. These addresses are not routable on the public Internet. Locally scoped, private IPs only function within a single private network and cannot be accessed directly from the outside world. Reusable, because they are not routed on the global Internet, the same private IP address ranges can be used simultaneously in millions of different private networks without causing conflicts. Assignment. A local network's router typically assigns private IP addresses to connected devices, computers, smartphones, printers, using the Dynamic Host Configuration Protocol, DHCP. Function with NAT. To access the Internet, devices with private IPs use a router that performs network address translation, NAT. NAT translates the private IP addresses into the router's single public IP address for external communication, and translates incoming Internet traffic back to the correct private IP address. Security. Private IPs offer an inherent layer of security by keeping internal devices hidden from direct Internet access, significantly reducing exposure to external threats. Reserved IPv4 private address ranges. The IANA has reserved specific IP address blocks for private use, as defined in RFC 1918, Class Address Range CIDR Notation Class A 10.0.0.0.0, 10.255.255.255 10.0.0.0/8 Class B 172.16.0.0, 172.31.255.255 172.16.0.0/12 Class C 192.168.0.0, 192.168.255.255 192.168.0.0/16. IP multicast address range. IP multicast addresses use specific, reserved ranges in both IPv4 and IPv6 to enable efficient one-to-many communication. These addresses are assigned by the Internet Assigned Numbers Authority, IANA, and are never used as source IP addresses in a packet. IPv4 multicast address range, Class D. In IPv4, The entire multicast address space is known as Class D and ranges from 224.0.0.0 to 239.255.255.255, or 224.0.0.0/4 in CIDR notation. This range is further subdivided for specific purposes: range description, routability, link, local control block, reserved for network protocols 224.0.0.0, on the local subnet, example OSPF, RIPv2, DHCP. These no 224.0.0.255 packets have a time to live, TTL, of 1 and are never forwarded by routers. Global scoped addresses, ASM, used for general multicast 224.0.1.0, data transmission across the Internet. Specific addresses in YES 238.255.255.255 this range are reserved by IANA for well-known applications, example NTP uses 224.0.1.1. Source-specific multicast, SSM, reserved for use with the 232.0.0.0, SSM delivery model, where the receiver specifies both the YES 232.255.255.255 group and the source from which it wants to receive traffic. Administratively scoped, private, reserved for private use 239.0.0.0, within an organization's domain. Routers typically filter these local-only 239.255.255.255 addresses at administrative boundaries, allowing organizations to reuse them internally without conflict. IPv6 multicast address range. IPv6 addresses do not use classes, but all multicast addresses are defined by the fixed prefix FF00:8, meaning the first 8 bits are always FF in hexadecimal. The structure of an IPv6 multicast address includes a scope field, which defines how far the multicast traffic is allowed to travel, scope value description, example address, hex, interface 1 FF011, all nodes on interface, local 2 link, local FF021, all nodes on local link, 5 site, local FF05101, NTP servers on site, organization 8 FF08:16, organization-wide scope, locally global FF0E:16, routable across the Internet. The most common link local addresses, such as FF021, all hosts, and FF022, all routers, are essential for local IPv6 operations, effectively replacing the IPv4 broadcast functionality.